So in this lecture, we want to talk about the integrability of functions with discontinuities. So as a sample lecture here, we want to make sure that we have some context for what you would have seen before this, and then what we're going to go on. So we would have seen the definition of integrability, right? That just means what a function is either integrable or not integrable, so we can calculate out that definite integral. And we would have seen that continuous functions are integrable. So what that means is that if you have a continuous function, you can always evaluate its definite integral and get a finite number, as long as you're integrating over a finite region. Now, it's more complicated if we're dealing with discontinuous functions. So you might remember from the derivatives part of calculus, if you have a discontinuous function, then it's not differentiable. For integration, it's more complicated. Some functions with discontinuities are integrable, where other functions with discontinuities aren't. So what we're going to see here is we're going to see an example of a function that has infinitely many discontinuities, which is integrable, and then we'll see another example of a function with infinitely many discontinuities, which is not integrable. And we'll talk about how we can actually prove that function is not integrable. So let's go ahead and put our goal in here. The goal is to show that some functions with infinitely many discontinuities are integrable, while others are not. So as you kind of go through this lecture here, we'll first talk about that definition of integrability, because we need to know what the definition is before we can actually prove anything, and then we'll see those different examples.
So the first thing we need to do is define integrability. So what does this mean, right? Integrability is just when a function is integrable. So when a function on a finite domain, so a finite interval as its domain, is integrable, or has a finite area under the curve that we can calculate. So we can actually define what the value of the definite integral is. So right, we're going to define what the value of a to b of some function f of x dx. So if I can actually define that definite integral, I call that function f integrable on this domain from a to b. You might have seen this definition of integrability before, or the definition of what that definite integral is before, as the limit of a bunch of Riemann sums. And the technique we're going to use is similar. We're going to use what are called step functions instead. And you'll see that they're a lot like Riemann sums, but what we're going to do is we're going to use something besides limits in order to do this. So before we get into that, let's go ahead and define what a step function is. So a step function is a function. So it's going to define to each element in my domain some sort of output, which is piecewise constant. So it's going to be constant on a bunch of different pieces on a finite number of pieces. So I can't just say, oh, well, there's infinitely many pieces and it's constant on each one. So finite number of pieces here. Okay, so what does that look like? What we need to do is we're going to draw out a little graph here. And I always want to be thinking of some finite domain. So I'm always going to have some a and b, and they could be positive or negative. They can be as far apart as I want. But I have some finite domain I'm going to start with. And then I'm going to take that finite domain and I'm going to separate it out into a finite number of intervals, so subintervals. This is called a partition. And if I have a step function, then that function must be constant, so take on a constant value on each of those subintervals. So it can take on any constant value I want. It can repeat constant values. It doesn't have to change when you move on to the next subinterval. And then another sort of fact about it is that at the endpoints of those subintervals, it's allowed to have whatever value it wants. So it doesn't have to be the value of the endpoint, but it can be if it wants. And obviously it's a function, so it only has to pick one value at each point. So I couldn't have it be the value of both endpoints. That's not allowed for functions. Okay, so we can sort of fill in the values. Maybe we have an open circle there, something like this, to get the values of this step function. And the nice thing about step functions is that if I want to find the area under the curve, so let's call this step function s of x, because s and step both start with s. If I want to integrate s of x to find that area under the curve, well, I know that each of these areas is just going to be a rectangle. So I'm just going to have a finite number of rectangles. I ignore the values of the function at the endpoints. I just think about the values on each of those subintervals. So I can define the area under a step function, or the definite integral of that step function from those intervals from a to b, as the sum of the areas of those rectangles. So it's going to be the sum from, let's say, I equals 1 to n. I'll call this my x sub 0, x sub 1, x sub 2, x sub 3. The value of the function on the first interval I'll call s sub 1. This one will have value s sub 2, and so forth. So let me just label those values there. So I'm going to do the height of that rectangle, s sub I, times the width of the rectangle, which is just going to be my x sub I minus x sub I minus 1. So, right, this is just saying that we need to make sure we calculate the length times the width, or sort of maybe the width times the height of each of these rectangles, and then add them up, and that's how we get the definite integral of a step function. Okay, so step functions are going to be integrable, and now if I have a non-step function, I'm going to use step functions to define the integral of that function. So how do we do that? So I'm going to look at the set of all step functions s that are below my function f. So let's go ahead and graph this out. Let's say I have a general function f here, and I want to find out its integral from a to b. So I can find a step function that sits underneath f. So maybe it looks like that. So it's a step function, and it's always underneath f. So I can go ahead and I can calculate out the area of that step function, the definite integral of that step function, and I get a value in my set. So maybe I calculate out this area. Maybe this guy had area 2, 3, 4, 3, 4. I add those up, 10, 16. So then in my set goes the number 16. Right? And then I find another step function that's also below f. Maybe this one's a little bit closer. It doesn't have to be over the same interval. I could make it over a different partition, whatever I want. And I find the area of that one. Maybe that's something like 18. I put that in my set. Once I have all of these infinitely many step functions that fit below f, I want to try to find the least upper bound of this set. So what does that mean? To be an upper bound, it has to be greater than or equal to everything in the set. So maybe 20 is greater than or equal to everything in the set, or maybe 25 is greater than or equal to everything in the set. But if 20 is greater than or equal to everything in the set, so is 25 and 26 and 27, and every number bigger than that. So I want to find the least of these upper bounds. And that's often called the supremum. So here, right, this is where I'm avoiding taking limits. I instead find the supremum, or the least upper bound, of the numbers in this set. And if we can think about that, right, that's going to sort of show us how much stuff I can fit below f, which should be a pretty good estimate of the area under f. But now we go over here to the other side, and we do the same thing. But now I want to find step functions t, where t is bigger than f. So I'm going to draw in what looks like approximately the same f, and then we'll draw in some step functions. And now my step functions are going to be above f instead of below f. They can be really close, they can be really far away, and I'm going to find the area there. So maybe this has area 28. I find a different step function which is also above. Maybe it has lots of little guys that are really close to f. And it has area 25. Right, so I find all of these values. And for this set, because it's above, I kind of want to know the smallest things in it. So I'm going to look for a lower bound. So something that's less than or equal to everything in the set. And then I want to look for the greatest one of those. So I'm going to find the greatest lower bound, which is sometimes called the infimum. Okay, so I do this whole operation. I find the set of step functions below and their areas. That's my S. I find the set of functions above and their areas. That's my T. I find the supremum of S and the infimum of T. And now, finally, let's put this over on the side here. If the supremum, the sup of S, is equal to the infimum of T, so if the biggest stuff that goes below is equal to the smallest stuff that goes above, then f is integrable. And if it's not, then f is not integrable. So that's the way that we can define integrability in this class and in this context. Now that we've seen our definition of integrability, we can move towards our main goal, which is to show that some functions with infinitely many discontinuities are not integrable, while others are integrable. So in particular, I want to show that this function f of x, which is 1 when x has the form 1 over n, where n is a positive integer, so let's make that z plus, and 0 when x is not of that form, is integrable. So let's actually think real quick about what that function looks like. When n is equal to 1, x is 1. So when x is 1, the function value is 1. When n is equal to 2, x is equal to 1/2. So at 1/2, I have a function value of 1. When n equals 3, I get 1/3. I have a function value of 1. 1/4, I have a function value of 1, and so forth. But then for all of the other points that are not of that form, I'm going to have a function value of 0. So I'm going to have an open circle at each of these 1 over n's, and then I'll have a value of 0 everywhere in between. So that function has infinitely many discontinuities because there's infinitely many times that it's going to jump up to 1 over n, because I have infinitely many positive integers n. However, it still is integrable. Now the second function here, g of x, it's 1 on the rational numbers and 0 on the irrational numbers, so if x is not rational. So this function looks kind of similar. So it's going to also be 1 at 1, and it's going to be 1 at 1/2, but it's also 1 at 3/4, 5/6, maybe 1 over 12 here, but also 3 over 23, somewhere around there. So it's going to have infinitely many times that it's 0 and infinitely many times that it's 1, just like the function above, but they're going to be sort of spread out more, right? I'm going to have all of these rational numbers where the function value is 1, and then all of the irrationals where it's 0. This function is not integrable, where the original function is integrable. So that's actually what we're going to see. We're going to prove rigorously that this function is not integrable. I'll show you some of the ways that you could think about proving that the first function is integrable, and then I'm actually going to leave that for you guys to think about. Or if you're interested, you can take the class and we'll talk about it more in the class. So let's go ahead and show that this function g of x is not integrable, and I want to think about it being integrable on a specific domain, so we'll say on 0, 1. Okay, so let's go ahead and sketch out a graph of this function, right? It's going to be 1 on all of these rational numbers. It's going to be 0 on all of these irrational numbers. I'm just drawing closed dots here, not open dots. It's kind of hard. If I draw them as circles, they might look like open dots. So I have this function on the interval from 0 to 1, and it's switching back and forth between 0 and 1 infinitely many times. So what I want to think about is I want to think about the step functions, s of x, where s is less than my function f. Right, so to have a step function, I have to have some interval here, some subinterval, some partition of my interval from 0 to 1. And then that function has to be constant on the interval. But if I look at any of these subintervals, we have this fact, and this is actually something that you would prove on your homework in this class, that at any open subinterval of the real numbers, there's always going to be both a rational number and an irrational number. So since we always have an irrational number in that subinterval, we need our s to be less than or equal to 0, as long as it's less than or equal to, let's put an equal to, f here. So I know that if I'm looking at my set s here of the integrals of functions from 0 to 1 of step functions, where s is less than or equal to f, I know that the number 0 can be in that set. That's when s equals 0 for every point. But nothing bigger can be in that set, because on every interval, my function value is going to be 0 at least once, because there's always an irrational number. I could have a step function that has negative values. So maybe I could have something like negative 10 in here, if I have a lot of big negative numbers. But remember, the thing I'm looking for in this set is my least upper bound. So it needs to be bigger than or equal to everything in the set. So, 3 is bigger than or equal to everything in the set, because it's positive and everything in the set is 0 or negative. So is 2, so is 1, but so is 0. Right, those are all examples of upper bounds. And the least upper bound of this set is 0. Anything bigger than it isn't the least, because it is an upper bound. Anything less than it can't be an upper bound, because 0 is in the set. So it must be my least upper bound. So the supremum of that set S is 0. And now for integrability, we need the infimum of the set of step functions above my function to also be 0. So I think maybe you can kind of predict where this is going to go, but let's go through and fill in the gaps. So again, I have my function f. Now I need these step functions t, and t has to always be above f. And I'm going to look at the set of integrals from 0 to 1 of these step functions t, where t is bigger than or equal to f. So maybe I have really big values of t and I get something like 12, I could get 15, or if t is always equal to 1, then I would get 1 is the value of that integral. But I can't get anything less than 1, right? T can't be less than 1, since on every subinterval, so if I have a step function, I have to have some sort of subinterval where it's going to be constant, but in every single one of those subintervals, there's both points where the function is 0 and the function is 1, because on every subinterval, there's always rational numbers and irrational numbers. So there's a rational, so it can't be less than 1. So this 1 is going to be the smallest number that I could possibly. Sorry about that. I'm looking for my greatest lower bound. So a lower bound, 1 is a lower bound. So is a half and 0 and -5, right? They're all less than everything in the set. But the biggest of those is 1, because anything bigger than 1 isn't less than everything in the set, since 1 is in my set. So my infimum of t is equal to 1. And then, since the supremum of s is not equal to the infimum of t, this function is not integrable. Okay, so last but not least, let's think about some ways that we can show that the function, which is 1 on numbers of the form 1 over n and 0 elsewhere, is integrable. So again, I want to kind of sketch this function out so we can picture what it's going to look like. I'm only looking at the interval from 0 to 1 here. So I have 1, 1/2, 1/3, 1/4, 1/5, and so forth. I have all of these points, and they're getting denser and denser as we get towards 0 there. That's where the function is 1, and then everywhere else, my function is 0. So we can tell here, right, basically there's these large swaths where the function is going to be 0. And that's what's going to allow this function, even though it still has infinitely many discontinuities, that's what's going to allow it to be integrable. So again, to show that it's integrable, we need to show the supremum of the set of integrals of step functions, where those step functions are less than or equal to f, is equal to the infimum of step functions, where those step functions t are going to be greater than or equal to f. So in fact, we are going to show both quantities are 0. Generally, when we're trying to show two quantities are equal, and this is a technique you'll get used to in this class, what we do is we show that their difference is 0. Because showing things are 0 is much easier than showing that it's equal to some other unknown quantity. But here, we don't even need to show their difference is 0. We can actually just show both of them as 0. And to show quantities are 0, let's say to show a positive quantity is 0, we show that it's less than epsilon, which is just some variable here, for every epsilon greater than 0. So basically show that it's smaller than any positive number, right? It's smaller than a half, it's smaller than a quarter, it's smaller than a fifth, it's smaller than any positive number, so it has to be 0. So let's kind of sketch this out by, let's say we want to show, for example, that the one that seems like it might be bigger, the one that's going to have these functions above, so I want to show that the infimum of this is, say, less than a quarter. So I want to show that I can get that my greatest lower bound is less than a quarter. So as long as I can show there exists some integral, let's say less than or equal to, which is equal to a quarter, then that means in my set is a quarter. So the lower bound has to be less than or equal to a quarter. So the greatest lower bound would also have to be less than or equal to a quarter. So if I can show that I can find some thing that gives me a quarter, some integral, some step function that gives me an area of a quarter, then I will sort of be able to show that I can get it less than a quarter. And then we change that a quarter maybe to an eighth and figure out how to get it less than an eighth. And hopefully at that point you can recognize a pattern, so you can replace this fixed number with a fixed but arbitrary epsilon and show that it's less than epsilon for every epsilon. Okay, so how do we go about showing it for a specific value, just to kind of get the idea? I'm going to take this quarter and I'm going to split it into two. So I'm going to have two pieces to work with, an eighth and an eighth. And what I want to do is, remember, I'm trying to find a step function here that is going to have area equal to a quarter. So the first thing I'm going to do is I'm going to find a rectangle of area 1/8, and I'm going to put it sitting here at 0, because that's going to allow me to include a lot of my points, because I know that most of my points are near 0. So I'm going to have a function height 1 out to the point 1/8. This is where our creativity has to kind of come into play. So here's a function of height 1, so it's bigger than or equal to the function, up to 1/8, and that's going to give me an area of 1/8. Now, which points are left? Well, there's going to be something at 1/7, because that's bigger than 1/8, and 1/6, and 1/5, and let's just pretend 1/4, 1/3, and 1/2. So, not drawn to scale. So basically, I count, and I have 7 extra points here that I still need to make sure I have rectangles around, right? Because in those intervals, my function value would have to have height at least 1, because the function value there is 1. So I'm going to take this 1/8 and divide it by 7. So I get 1/56. And each of those remaining little points is going to get a tiny little rectangle around it of width 1/56. So that when I add up all 7 of them, that's still going to give me a width of 1/8. So by doing this, I'm building a step function which is greater than or equal to my function at every single point, but it's going to have area equal to 1/4. Now you would have to kind of think about how to generalize this argument for an arbitrary epsilon. So if I have a fixed but arbitrary epsilon, so some number that we don't know what it is, but we know that it's greater than 0, how can you change this argument to be able to build a function that has area less than or equal to that, so that the greatest lower bound of this set is less than or equal to every positive number, therefore we could prove that it's going to be 0. Then you would also have to show that the supremum of this set is 0, and that would be your argument. So I'm going to leave that for you guys to think about. Hopefully this gives you some ideas of how this class is different than a standard calculus class, and how we would go about proving these sorts of things and what a proof looks like.